So in chapter 6, what are special, cases or conditions that we want to talk about? Well, one is the ballistic pendulum, and then of course another one is a rocket. I'll just talk about the ballistic pendulum right now, and then the rocket in a moment. So if you have a bullet that's going towards a block, and let's say it does get embedded inside the block, it could go through the block too. That would be an inelastic collision if it embeds in it, and elastic if it does go through. I suppose it's perfectly inelastic, but if it does go through, usually there's quite a bit of kinetic energy loss when it just goes through, so it's not going to be perfectly elastic. Well, let's take a look at the inelastic condition. So the bullet does get embedded through, and it's our job to figure out what the beginning velocity of a bullet is or how far the block goes up. So in this case, we know the velocity of the bullet, and it gets embedded in here. We'll just kind of draw that in there a little bit, and then this ballistic pendulum will swing upwards, okay, to a final height. Let's call this height final. Of course, the beginning height here, height initial, is going to equal 0 meters. Okay, and the way we do this is we look at, again, the inelastic collision, first of all. So we will have the mass of the bullet being m1, and the mass of the ballistic pendulum being m2. So then this equation would look like m1 v1 plus m2 v2. Okay, and this, of course, this v2 is going to equal 0 for it. It's not moving initially. And that'll equal m1 plus m2 times one common final velocity between the two of them. Okay, and of course the mass of the bullet is going to be quite small, but we'll still add it into the mass there. Okay, and then to figure out how high this goes, then once the bullet is embedded, we have a kinetic energy, and that'll go to gravitational potential energy. Okay, because we're going to a final height, so we'll do 1/2. In this case, we'll have m1 plus m2 times the common velocity right there that we found, and it equals m1 plus m2 times a final height. And once we find the final height, then we're done. Now again, we could go backwards. We could have the final height initially, and then we can go from gravitational potential energy to kinetic energy as it goes back down here. In other words, it got struck, it swung up here. We need to figure out, okay, what the velocity here is. That's this velocity. You just go backwards and find velocity 1 there. Okay, now what about another special condition? Okay, what if we have a door looking at the top view, and it's going to be struck by a piece of putty or something that's going to stick to it? Okay, or it even could bounce off it. It really doesn't matter. So we're going to do a conservation of momentum, okay, before and after this collision. So again, momentum 1 must equal momentum 2. Let's assume the door is not moving, so all the momentum initially, okay, comes from the putty. But once it hits and sticks together, the door will actually swing. Okay, if the door swings down, we have angular momentum. So what's the relationship between linear momentum and angular momentum? Well, L turns out to be equal to the momentum in the linear sense, okay, multiplied by the distance you are to the point of rotation. So I'll say multiplied by the distance, and I'll remind us that that's the perpendicular distance. Okay, because whatever is perpendicular to the door here, this will be the distance d here. Okay, so I'll label that this way. How far the piece of putty is, okay, from the point of rotation here. So basically what we're going to end up having in this question here, and let me put vector hats on these again, we'll actually have L1, the angular momentum of the putty before it hits the door, is going to equal L2. Okay, once the putty hits the door and it starts to swing. Well, remember, L is equal to I omega, and I being the moment of inertia of the object multiplied by the angular velocity. So we're actually, this equation is going to look like this. We're going to have momentum 1, which is the momentum, okay, of this particular piece of putty, okay, multiplied by the distance it is to the point of rotation, and that'll equal moment of inertia total, I'll say I1 plus I2 multiplied by omega. Okay, so what does this mean? Well, we would have a mass times velocity for this putty coming in, so 1.2 multiplied by 30 times how far this is from the point of rotation. Okay, that's what this represents. And then I1 and I2, we'll have a moment inertia for the door, because it's about to spin. And then we'll have to have a moment inertia for a piece of putty stuck in there too. The putty will be a point mass rotating around, and the door will have its own equation, and multiplied by omega, which is a common velocity that both of them have. Okay, now if this putty happens to bounce off, then you have an elastic collision, and then it does involve assistance of equations for that. So we'll keep it simple today and make it an inelastic collision where it actually sticks to it.